with electronegativity, actually, let me welcome everyone to this lesson. Actually, this is my first time to do welcome, because whenever I begin recording, and so let me welcome everyone to this lesson. So we've had a review from our previous lesson. Yes, Innocent, you've told us where we are and what transpired in our previous lesson, and where we saw different periodic properties such as electron affinity, bond energy. We saw boiling point, how boiling point varies within these group 7 elements. And now let's talk about electronegativity. So the general trend, generally, electronegativity decreases down the group, with fluorine having the electronegativity that is abnormally high. Okay? It is abnormally high compared to the rest of the group members. But the trend is the same. Okay? Down the group, the atomic sizes of these elements keep on increasing. Okay? The atomic radii of these elements keep on increasing. And so what does that mean? It means that why is even the size increasing? Because the electron is added on an extra energy level. Or from maybe fluorine to chlorine, there is always that extra shell that is added. From fluorine to bromine, there is that extra shell that is added. And from bromine to iodine, there is that extra shell that is added. And so as a result, the sizes keep on increasing down the group. And so if the sizes increase, then what will happen to the effective nuclear charge? The effective nuclear charge will decrease, decreasing the effective nuclear attraction for the bonding electrons. Okay? These two electrons that are used in formation of a covalent bond. Okay? So if you decrease the nuclear attraction for these bonding electrons, then the overall electronegativity is going to decrease. Now fluorine has an abnormally high electronegativity because with fluorine, if you compare its charge density, if you compare its size, it has a very small atomic size. Okay? Very small, with very many lone pairs of electrons. Okay, the fluorine is small, okay? So the bonding electrons, they will be too close to the nucleus. Too close to the nucleus in fluorine than how the electrons are close in chlorine. And so as a result, if fluorine bonds to any element, maybe this is fluorine and this is another element that fluorine is bonded with, okay? The bonding electrons, the two electrons in this bond, they will be strongly attracted to this nucleus of fluorine, which makes it have an abnormally high electronegativity compared to other group members. So basically, like I told you, I always say this. Electronegativity, in organic chemistry, once you understand the periodic properties, then inorganic chemistry becomes so easy. You just remain with writing equations and some few concepts. If somebody has a question, it's okay. So you just remain with writing equations and some few concepts. Okay? And you're done with inorganic chemistry. Now, with electrode potentials, okay? Now, what are electrode potentials? These are, you can define it, we shall study it in physical chemistry in electrochemistry and electrochemical cells. And you see that the electrode potential, it is the electromotive force, the EMF of a cell, okay? And it is usually determined as a reduction potential when a particular cell is connected to a She standard hydrogen electrode. So I won't talk about all this, okay? We shall reach there and study it, that is if time allows. Now that overall EMF, okay, of a given electrode is what we call the electrode potential. And what factors affect electrode potential? Number one, we have atomization energy. Actually, we studied this in physical chemistry. Then number two, you have ionization energy or electron affinity. And number three, enthalpy of solution. And overall, you produce electrons that will move. Okay? Then when electrons move, then current will move in the opposite direction. Now it is that current that will be measured by a voltmeter, okay, to give you the electrode potential. Now, for these halogens, the reduction potentials become less positive as you go down the group. They become less positive as you go down the group. What does that mean? It means that the oxidizing power of these elements decrease down the group. Okay? And so chlorine, which is more powerful oxidizing agent, is going to have the highest electrode potential. Okay? So the more the negative, the electrode potential, we shall study all this in electrochemistry. That's where we shall enjoy. But the more the negative, the electrode potential, the strongest reducing agent. And the strongest reducing agent is the one that gets oxidized. Now there is, okay. It is the one that gets oxidized within a redox reaction. And the strongest oxidizing agent is the one that gets reduced. Okay? And so when you have more negative, if you are given electrode potentials, you choose the one of the two electrode potentials, which one is more negative. If they are all negative, if they are all positive, which one is more positive? Sorry, which one is more negative? If one is positive and another is negative, then that is obvious. You choose the one that is more negative. And the one that is more negative, then it is the one which undergoes oxidation. So it is the one which is a reducing agent. But for the one that is more positive, then it is the one that gets reduced. So it is the one that is an oxidizing agent. So now, if they become less positive down the group, what does that mean? It means the oxidizing power of these halogens keep decreasing as you go down the group. And so they are the electrode potentials that can give that. So high oxidizing strength of fluorine is favored by, yes, we have seen that since fluorine has a high electrode potential, and we have concluded that fluorine is a high oxidizing agent. Why is fluorine? Actually, of all things we've been studying, you talk about this and you'll be like fluorine. You talk about that and you'll be like fluorine. This fluorine. Why fluorine? What is bringing about the difference in chemistry of fluorine? Okay? Now I think you should have some answers in your mind. You should be thinking of some answers in your mind. So number one, Fluorine has a low bond dissociation energy. If you are to compare, this is one fluorine, okay, and this is another fluorine. Since they are small atoms, you can see, very small, okay, you may assume, they are small atoms, you may assume that the atoms are close together, so the bond is strong, so the bond dissociation energy is going to be high. From physical chemistry, remember that. But for fluorine, it's a special case. It is the reverse. Why? These small atoms, okay, they will have the electron density. Remember fluorine, it has 7 electrons in the outermost shell. So you have used just one. So you remained with a lone pair, 1, another lone pair, 2, and another lone pair of electrons, 3. Maybe for those who are absent, this is how we can illustrate that. So this is the P, okay? So you have used, this is fluorine, this is another one, and then this is another one. And since you have 7, then you have this, and then this, okay? So you have used this to overlap, okay, to form a covalent bond. So the same fluorine has 3 lone pairs of electrons, okay? This one will have this, and this. Yeah, you have 2 here. Okay, this is 2, this is 4, 6. Yeah, you have 2 there, and the same, you have 2 here. Okay, you have 2 there. So these 2, 2 lone pairs, let me remove one, sorry for that, and another 2 lone pairs of electrons, okay, on another fluorine atom. So the lone pairs of electrons, they will repel each other, okay, they will repel each other, creating that force of repulsion between the lone pairs of electrons will extend this fluorine bond, which makes it weak to be broken. So we explained that in our previous lesson, okay? And so if you are to check on the bond dissociation energy of fluorine, is going to be low compared to chlorine and other halogens. Then another factor, we almost explained all this, enthalpy of hydration, so high, the atoms are small. Let me illustrate that. The atoms are small, okay, small atoms. So when these small atoms with a high charge density get surrounded by water molecules, okay, when the water molecules, for those who attended our thermochemistry lessons, you know that. So for these small molecules, when they get surrounded by water molecules, too much energy is going to be released when finally these water molecules have successfully surrounded these ions. So now that too much energy is what we refer to as hydration energy. And for fluorine, it has a high hydration energy. Okay? And so because of that, it makes fluorine to be kinda unique. Absence of enthalpy of fusion and vaporization, or enthalpy of atomization. Now for fluorine, you don't need to atomize, because does it exist as a diatomic molecule? Find out. Okay? So since you don't need to waste energy to convert the fluorine molecules into atoms, then it creates some uniqueness, okay, in the chemistry. So because of that, then you have a high oxidizing power. You be a high oxidizing agent that when you react with any element, the element will always react with you using its maximum oxidation state. Now, why does it behave differently from the rest of the group members? High electronegativity compared to the rest, small atomic radius compared to the rest, which leads to this, and hence, then low bond energy compared to the rest. We saw all this from the table. And finally, high electrode potential, which is highly positive compared to the rest. So, I hope that one is okay. In case you have a question and you feel the question is immediate, it's okay. You can unmute and ask. But if you feel the question is not immediate, then it's okay. You can drop it in the chat box. I'll find it. Okay? Yes, now let's see the special properties, special reactions of chlorine that are different from other compounds. Number one, fluorine can combine directly. Maybe let me use this. It can combine directly with carbon at room temperature. Can you imagine? To form tetrafluoride or tetrafluoromethane. Can you imagine? Fluorine combining directly with carbon at room temperature. No need of somebody has joined or I've lost connection. I'll see it from here. Combining with carbon at room temperature to form carbon tetrafluoride. No need of heating. Is it a gas? I think it's a gas. No need of heating. Okay? It occurs at room temperature. So that shows that really it is highly reactive compared to other members. Number two, fluorine has a high boiling point. Very high boiling point. Not fluorine but hydrogen fluoride. Like I told you, if you had to compare the hydrides of group 7 elements, we shall study them. You find a boiling point of hydrogen fluoride kinda here. Then drop, and then this is the boiling point of hydrogen chloride, and then some gradual increase to the boiling point of hydrogen iodide. So such a trend, okay? The fluorine, the boiling point of its hydride, so high, abnormally high, okay? Compared to other hydrides. So how can you account for that? Now, I'll take you back to our lesson where we studied bonding, okay? Where we saw that where hydrogen is directly bonded to fluorine, or hydrogen directly bonded to oxygen, and hydrogen directly bonded to nitrogen. Then these molecules, they will form what we call intermolecular hydrogen bonding, or hydrogen bonds. So it is the same case here. The hydrogen fluoride, the molecules of hydrogen fluoride, very many molecules of hydrogen fluoride, they do exhibit hydrogen bonding, where fluorine is more electronegative than the hydrogen. So it will attract the bond, the electrons within this hydrogen fluoride bond, to become partially negative and hydrogen partially positive. So when the molecules of hydrogen fluoride, very many molecules, okay, the same case, oh sorry for this is negative, and then this and then this one is partially positive, and then you have another one, hydrogen fluoride. So if many molecules of hydrogen fluoride come together in a solution form, then they would exhibit what we call hydrogen bonding, or intermolecular hydrogen bonding. Now there are these hydrogen bonds that are too strong, okay, to break, hence making hydrogen fluoride to have a high melting and boiling points. But the rest, you can see from chlorine to iodine, Now these hydrides, they do not exhibit hydrogen bonds, but rather weak van der Waals forces of attraction, because they form simple molecular structures. These are simple molecules. Okay? These are covalent molecules. So they form weak van der Waals forces of attraction. And so, what does that mean? The magnitude of these van der Waals forces of attraction increases with molecular mass, which accounts for now the increase in boiling point. But for this one, it's abnormally high compared to the rest of group 7 members. Is that really okay? That's brilliant. Let's check on another property that makes chlorine different from other members. The hydrofluoric acid, HF, hydrogen fluoride, dissolved in water. It's a very weak acid. So weak acid. Why? Because the hydrogen fluoride bond is strong to be broken. Too strong to be broken to release hydrogen ions in aqueous solution. And so what does that imply? It is going to be a weak acid compared to other halogens. HCl. Now this one, it is really it's a strong acid. Hydrogen bromide. You really know. Hydrogen iodide. Now these are strong acids. But for hydrogen fluoride, because of this bond, hydrogen fluoride bond is too strong to be overcome, to be broken. Then in aqueous solution, it will release few hydrogen ions in aqueous solution. And so as a result, it becomes a weak acid. However, if you dilute, then you can increase on the acidity of that solution, unlike others. Is that okay? That's brilliant. The silver fluoride is soluble in water. The silver fluoride, if you've been attending, you can now know why it is soluble. Hydration energy of fluorine is high to overcome the lattice energy. But the rest, the silver chloride, the silver bromide, the silver iodide, insoluble in water. But for silver fluoride, the fluorine, like what we have said, it has a high hydration energy. So high hydration energy that this will end up becoming, the enthalpy of solution is going to end up becoming negative. Hence silver fluoride becoming soluble in water. So the rest is just normal business. There is nothing different here now. The rest is just normal business. Fluoride has only 3 oxidation state. Only 1, not 3, it's only 1. Whereas the rest of the members, they have variable oxidation states. For example, haven't you ever seen such compounds? You have this, and then you have this. Haven't you ever seen such compounds? And then you have this. So now these are chlorides in different oxidation states, where this one is in +6, this one is in +3, whereas this one is -1 oxidation state. So because of that, then fluorine becomes different. It isolates itself from the rest of the group members. Then fluorine does not form oxoacids. Yes, the same way I said. The oxoacids, they are these ones. The chlor, then 3. These are the oxoacids. If you put H here, then that's an oxoacid. So you cannot find fluorine in this nonsense. Why? Because it has a powerful, it is highly oxidizing agent. Okay? It cannot do this. That's why it even has 1 oxidation state. The electrons on fluorine are strongly bound. They cannot just be easily donated. Okay? And so as a result, you have just 1 oxidation state. Then the calcium fluoride is insoluble in water, whereas other halides of calcium are soluble in water. And yeah, basically that's fluorine. So for those who have been asking that why fluorine, why fluorine, why fluorine, you now have the answers. You now have the reasons. You now know why the chemistry of fluorine requires enough attention. So now, okay, so from what we have discussed, you have seen the uniqueness of fluorine in its chemistry. And actually, all these reactions that we are going to talk about, you see that really fluorine is different. Fluorine is on its own. Whereas other members are reacting in this way, for it will be reacting to form this and this. Whereas other members are reacting to form this and this, for it will be forming. So it is on its own, indeed on its own. And I hope by now you know why fluorine is on its own. So let's start with reactions of halogens with water. Now this is the real inorganic chemistry. You need to know how different elements react with other compounds. Okay? And the first one is water. Like as usual, it is a special case. Whereas other elements are reacting with water to form hypochloric acid, or we are going to see. For it oxidizes water and the reaction is vigorous. Okay? To oxygen, and then the fluorine is reduced to hydrofluoric acid. Okay? The reaction is vigorous. Whereas other members, okay? We are going to see how other members. So this is fluorine, okay? And it's a gas reacting with water. You can write the equation with me. And the water is a liquid, okay? So we shall form the hydrofluoric acid, HF, okay? HF, and this is aqueous, and oxygen is evolved, and oxygen is a gas. So it is as simple as that. Can you try to balance that equation? So if you put a 2 here, and a 4 here, what shall we get? So it's okay. Now with inorganic, you must write an equation and you balance it. So put a 2 here, and you put a 4 here, and a 4. Okay? So that is the equation. So, whereas now no other member can oxidize the water to produce the oxygen. But for it will oxidize the water to produce oxygen. Is that okay? Anyway, that one is some simple stuff. Let's talk about other elements. Now with other elements, for example, chlorine, bromine, they will react with water to form the halic acids. The halic 1 acids, or you can call them hypohalic acids. You did this reaction in order. You can say, for example, okay, let me generalize X, okay, and this is a gas. You did this reaction in audible plus water, water, and the water is a liquid. Then we shall form. Now this is in organic chemistry, you can't run away from equations. Then we shall form our halic acid X. Is it XOH? Hypochlorous. It is HCl. Yeah. So I can use this X and then HCl. HX. Now I can't rub. So it is HX. And this is aqueous. Okay? This one is also aqueous. So can you try to balance that equation? Balance.
Teacher,
Yes?
I thought it is HOX,
HOX,
the hypochlorite.
the order doesn't matter.
Yes.
The order is the same. But it's okay. You
Okay.
can write HOX or XOH. It is still the same. Whether you write it this way, so the order doesn't matter. So here, where X can be, X can be the Br and the Cl. So it is as simple as that. Is it balanced? Okay. So anyway, it is balanced. You can have, there is one H here, there is another H, there is O here. So it is balanced. So now this is bromine and chlorine. For them, when they are dissolved in water, you form a hypohalic acid or a halic 1 acid. Why this? Now, when you expose, you studied this reaction in oil. When you expose this hypochlorite acid, for instance, and you expose it to sunlight, then it will dissociate, okay, to produce the oxygen gas. I think the reaction, and you can write the reaction, the equation of reaction. So in presence of sunlight, the halic decomposes to produce the oxygen gas. Can you write the equation? I know you are writing. Write the equation. Okay. HOX, it will decompose aqueous to give the oxygen gas, to produce oxygen gas, and the HX aqueous plus the oxygen gas, and this is a gas. Try to balance. If you put a 2 here and a 2 here, it is balanced. So basically that's how simple it is. Maybe for fluorine here, it is also diatomic, so you can write F2, okay, instead of just writing one F gas. So it is diatomic. You can write F2 and continue with your equation. So basically, now how about iodine? Now for iodine, it is insoluble in water. Okay? It is insoluble. If you dissolve iodine in water, it won't dissolve. Why? Because I think having that large size, okay, then the atoms are really non-polar, that they cannot easily interact with the water molecules. So it is sparingly soluble. Now, however, if you use potassium iodide, then the iodine is going to dissolve. Why is it dissolving? Because it is forming a complex. Okay? A complex. Which complex? Of triiodide. For example, I can illustrate, get some pen and write here. So you bring your iodine, okay, and it's whether gaseous, whether aqueous, and you add it to potassium iodide, okay, potassium iodide, then you form a complex of triiodide complex, this one. And now this one, it is the one that will be soluble, okay. And then if you want to titrate, then you can titrate that with, so you can, this reaction is so good in chemistry practical, this reaction so good in chemistry practical, okay. Yes, where in now the complex form, you can titrate it with sodium thiosulfate, and then you do back titration, you do calculations backwards, okay. So how about alkaline solutions? Still our special case, fluorine. Now with cold alkaline solution, fluorine reacts to form oxidifluoride and a fluoride plus water. It reacts with, it is still our special case. You need to know how special this guy is so that you can give him maximum attention. So fluorine, okay, gaseous, it will react with our OH ions, okay, with our alkalis. Now this happens in cold dilute alkalis. And this is alkalis. So what shall we form? We shall form our oxidifluoride, which is, you can write it as F2O, or you can say O and then F2. So what is easy for you? And then this is it aqueous or it's a gas? Maybe I will confirm the state. And then a fluoride, maybe it is sodium fluoride, or maybe depending. So a fluoride, and this is aqueous, and then water, and this is a liquid. Can you try to balance that? Yes, hurry up and balance. How far? Uh-huh. Okay. So anyway, this is a gas. So if we try to balance, I have two. So if I put a 2 here, and then a 2 here, and a 2 here, will it make any sense? Yes, it will. And a 2 here. So now the equation is now fully balanced. So you know the products. That is the the basic. Know the products, and after knowing the products, then the balancing and writing the equation, it will become easy for you. So with cold dilute alkalis, we shall form an oxidifluoride gas. Okay, you can write it in this format, or it is still the same thing, F2O, or you can say O F2, and this is a gas. Okay, then with a fluoride, maybe it is sodium fluoride or potassium fluoride, depending on which alkalis you've used, plus the water. Now that is fluorine, which is a special case. But now, how about our other? Now all of them, the rest, they will react with cold dilute alkalis to form a halide, but it's halite 1, and water. So it is as simple as that. Okay, I can represent it as X, and this is a gas, and this gas reacts with our cold dilute. Now, please, this is cold dilute. We also have with hot concentrated. Okay, and this is aqueous, and they are all different. Okay, so we shall form a halide. Okay, this is minus, and this is aqueous, and then a halide, this is X minus, depending on if you use sodium hydroxide, then that one becomes sodium halide, then this is aqueous, and the water, H2O, and this one is a liquid. Can you try to balance? Yes, use this chance to do the balancing. And the X is iodine. Now when you are in an exam, you are free to write this one also. Bromine, but make sure you are free to use X, but make sure after you define what X is. Is it your X, or it is the X that we know? So if you do this, you'll be good to go. Have you finished balancing? Maybe the X, they are balanced, the hydrogens not balanced, so we shall need a 2 here, and probably a 2 somewhere. No, there is 1, it's okay. I think now it's balanced. Yeah, it is now balanced. So our equation is kawa. Our equation is now okay, because the charges are balancing and everything is balancing. The equation is okay now. Okay? Yes. Now, if you fail states, you're doomed. If you fail the equation writing it, you're doomed. If you fail to balance it, you are also doomed. Okay? So you should be as careful as you can. Now that is with cold dilute alkalis. Now, how about with hot concentrated? Still our fluorine is a special case. That now here, instead of forming oxidifluoride gas, we shall form oxygen, a fluoride, and water. And this is that simple. Can you write the equation? Write it. Try to write the equation. Hurry up.
Teacher,
Yes.
you write for me sodium halite, halite,
Sodium halite.
halite,
Halite. So you want sodium halite, eh? Halite or halide?
halite.
Okay, a halogen is X. I can represent it as X, where the X
One,
can. Wanje?
not in iron form, in molecular form.
In the above equation for this one, eh?
Yes.
Okay. So this one is going to be a halite. Okay, let me first do the rubbing. So this one is going to be, meanwhile you are writing that. So this one is going to be sodium hydroxide, and this is aqueous, reacted with a halogen, and this is gas. So we shall form our sodium. I can put 8. I'm using X, so I can put my X here. Or I can put, now if I rub, okay, I will write it as sodium, or X. Now this is confusing. I can write sodium X and then O. So but they are all the same things. Okay? If you write this, or whether you write this, it still remains the same thing. So I can write XO, and this is aqueous, and then plus sodium chloride, so sodium halide, okay, and then aqueous, and then plus the water molecule. So that's what you wanted, and this is a liquid. Where X, where X can be chlorine. Actually, you don't need to put that too. Where X is chlorine, Br, and I. So if you put the 2, it means you just carry 2 and put the 2 here with these 2, and it becomes ambiguous. So just say X is Cl, Br, and I.
Teacher,
Mm.
I didn't know what halite one was.
Hey. So halite 1 is this, the halite, this one. Okay? Because if you are to calculate the oxidation state of chlorine, it's 1. Let's do it. It is XO with 1 minus. So if you assume the oxidation state of chlorine as X, of this halogen as X, and then plus the oxidation state of oxygen as -2, okay, it is equal to -1. So this, if we take this one this side, then the X remains with the oxidation state of +1. So that's why it is halite 1.
Teacher,
Yes?
that means in case of chlorine, that's a chlorate.
Yeah, that's, no, chlorite, not chloride. Those two are different.
Chlorate.
Chlorite.
Chlorite.
Yeah. Is it the accent? Chlorite. I hope that one is okay. If it's bromine, then that is bromide, not bromate. If it is iodine, then iodide, not iodate. I hope it is okay. How far with this equation? So it is fluorine, and the fluorine is a gas reacting with the OH. So it's up to you. You write what is easy for you. If you want to write the ionic equation, it's okay, you can write it. If you want to write the molecular equation, it's okay, you can also write it. So fluorine plus OH, then we shall form a fluoride, minus, and this is aqueous, and then we form oxygen gas, okay, and this is oxygen, and oxygen is a gas, and we shall form the water, okay, and this is the water, and the water is a liquid. Yeah, sorry for this. Anyway, I can remove it, it's okay. So this is water, okay, and the water is a liquid. So balance. So I'm seeing 2 fluorides. If I put a 2 here, let me use this yellow pen to balance. So I'm seeing 2F. So if I put a 2 here, and therefore I'll put a 2 here. The hydrogens, 2, they are okay. Oxygens, they are 3. Oh, so oxygens are bringing trouble. So it means I'll need to change. So if I put a 2 here, oxygens, they are 4 this side, and I put a 4 here, okay, and I put a 4 here, and I put a 2 here. so it will be balanced. Yeah, so now it is balanced. Okay, so it is 2, 4, 4, and 2. So these ones are not there. Okay, these ones are not there. So it is as simple as that. Now let me give you a trick. In inorganic chemistry, when you write an equation and it fails to balance, then you know that your equation is either lacking something. But it's not always the case. But 99% of equations that fail to balance, it means the equation is lacking something. But however, it is not a guarantee that when you write an equation and it properly balances, then it's not a guarantee that the equation is correct. It can balance when it is wrong. So how about the rest? Now the rest form halides. And then halite. Now halite 5. Okay? And what? And you can write this equation. This is not hard. It is not hard. Let's write it here. You form, I have x, oh, yellow.
But excuse me, sir.
Yes, innocent.
Was that equation the previous one? The ion.
Yes, you can ask your question. You've disappeared.
Oh,
Yes, innocent, you can ask.
but I remember you had the two.
I
Yeah,
can
it was two,
I
two.
I can rewrite the equation.
Yeah, let's rewrite it.
The one of this one, eh?
Yeah, the one of hot concentrated alkali.
With fluorine, eh?
Yeah, that one.
I formed
Mm,
it was fluorine, okay? And this is
then
gas,
plus OH.
then plus
Mm,
OH, okay, minus, and this is aqueous. Then I get oxygen, I get a fluoride, this is minus, then I get oxygen, okay, oxygen gas,
mm,
and then water. Not so?
yes.
So what's your concern?
Yeah, you had balanced as two on fluorine, two on hydrogen, on hydroxide ions,
No,
then
I changed it. I put 4 here, I put 4 here, I put 2 here, and I also put 2 here.
yeah, it's okay now. It's okay now.
Okay, so let's proceed. Now, have you finished writing this? You write this. Hurry up. So, let me write it. Let me write it meanwhile, as you guys you are also writing. So here it is equations you write and balance. And know how. You know that with cold dilute, you will form oxidifluoride. Then the rest they give halides. You are done with that. Then with hot concentrated, you form oxygen. Then the rest they give halides. And you are done with that. So let's see. We shall write X, okay? And this is a gas. And the X plus our hot concentrated alkalis, okay? And this is aqueous. Then we shall form a halide. This is X aqueous. Then a halite, not halide. And this is how we write halide. Now I'm going to calculate for the oxidation state. But I taught you how to calculate, but then we shall do. And then water. And then water. And the water is a liquid. So this is halite 5. It is in +5 oxidation state. If you assume this to be unknown, so this is x, and the x plus 3, 3 times -2, okay, should give us -1. So really this is simple math. So this one becomes x minus 6, which is -1. So x becomes therefore +5. So it is as simple as this. So that's why it is called a halite 5. So the halogen is in +5 oxidation state. That's why with chlorine, you remember, it has 1 oxidation state. It doesn't form this katogo. No, it doesn't form this. For it is in +1 oxidation state. But here now, say you have a halide. You see, you have a halide. And now now you have a halide. Now what is that? Let's balance. Let's balance. So halogens, I have 2 here, 2 oxygens. Oxygens will bring issues here. So this side I have 4. So if I put a 4 here, oh, that's too much. So if I put a 4 here, the oxygens there are 4, and I put a 3 here, okay, and I put a 3 here, and obviously I'll put a 2 here, and oh, no, it is not. So this is wrong because of this. So if I put, I'll need to put a 2 and a 2, so the hydrogens and a 4. Now if you put a 4, the oxygens, they are many. Who has finished to balance it? If we put a 6, okay, who has finished to balance it? It's going to take our time to balance this. You mean no one? Okay, if I put a 6 here, for instance, oxygen there are 6. This side, so I'll need to put a 3 here. So the oxygens there are 6. 6. Okay, yeah. So to balance the charge, I'll need to put a 5 here. And they are 6. Yeah, so it is balanced now. So put a 6 here, and a 5, and a 3, and a 3 here. So the equation is now balanced. Okay? So these ones are not there. So balancing equation involves a lot of effort, where you observe, okay? You look at a you look at an equation, and you balance accordingly. So that's our equation. Where X is chlorine, iodine, and Br. So you don't write the 2. If you write 2 here, it means where there is X, I'll just come and put Br2, okay, and then with the other two, and now this is just confusion. So just write X is Cl, I, and Br. So that means that where there is X, you can put this, or you can put this, or you can put this. Is that okay to everyone? If you want to ask, it's okay, you can unmute and ask. Maybe let me check the chat box. Okay, so basically that's how it is. So you have the 6 here, and then the 3 here. I don't have the 5 here, why not? The charges, this is 6, so I'll need the 5 here. I'll need the 5 to balance the charges, and then because see, this is 6, and if you don't put the 5, this will remain unbalanced, so there is a 5. Okay, yeah, that's good. So I'll change this. With hydrogen, now now this is the easiest. Now for fluorine, still it is a special case from others. My God, whereas others you need to do some heating. For this one, when you just mix it with hydrogen, boom, it explodes to form hydrogen fluoride. Okay, in as long as the hydrogen is dry, so you don't need to do the heating. Okay, hydrogen gas plus the fluorine gas, and they are mixed, then you will form your hydrogen fluoride gas. Unlike others, oh my God, what is wrong with others? And you put it here. Unlike others, this one can occur even in a dark room. But now for others, the chlorine, the bromine, chlorine, for instance, reacts vigorously with hydrogen in presence of sunlight, or you can say UV light, to form hydrogen chloride. And if you want to check on the reaction, free radical. Now for others, bromine reacts with hydrogen, but you must heat up to that temperature. Even you must apply a catalyst. For iodine, you must heat at that temperature. So do you see the trend? Do you see the trend? With this one, it occurs even in darkness. Okay? But with this, now it occurs in, it needs some light. Now here, if you just provide the light, it cannot. Till you heat up to this. Okay? Now with iodine, for it, you need to heat up to 400. And man, this is too much. Okay? So the reactivity decreases down the group. Okay? The oxidizing power decreases down the group. Now let's talk about oxidation reactions, since they are highly oxidizing agents. Then they can oxidize elements, okay, in their solution forms to form elements with high oxidation states. For example, when you bubble chlorine, okay, in a solution of tin 2 chloride, it turns to tin 4. The dice solution of tin 2 ions, it turns to tin 4. Hydrogen sulfide, it is oxidized to, the sulfide is oxidized to, the sulfide is oxidized to sulfur. Okay, and you deposit a yellow solid in case they want an observation. Sodium thiosulfate, still you to form different products. It will be oxidized. Let's write some half equations here. So we have our tin 2, okay, our tin 2 ions, okay, where they will be oxidized. Now here let's use half equations to tin 4 ions, but to balance the charge, you can see here it is plus 4, here it is plus 2. So to balance the charge, we shall put 2 electrons here. For chlorine, it is chlorine, okay, to give us, okay, the 2 chloride ions. 2 chloride ions. To balance the charge, we shall need a 2 here, okay, plus 2 negatives, 2 negatives, so it is balanced. So when we cancel this with this, then we shall remain with the tin 2 ions, aqueous. That's the first mistake. You can't forget states. If you dare, then you lose marks, aqueous. If you dare, this is gas, this is aqueous. Plus chlorine gas, to give us tin 4 ions, aqueous, plus the 2 chloride ions, aqueous. Okay, so this is one of the oxidation. Now in this, the chlorine is an oxidizing agent, because in the reaction it is the one which is getting reduced. You see, from 0 oxidation state to -1. You see, this one is 0 and this one is -1. So it is reduced. But for this one it is oxidized. So it is a reducing agent. You see, from 2 plus 2 to plus 4 oxidation state. Okay? So this one is oxidized and this one is reduced. You can also write for hydrogen sulfide. Let's write for thiosulfate. Thiosulfate is written as, okay, let me get some, it can't, yellow in yellow, I don't like it, because usually my titles are in yellow and I again use yellow. So thiosulfate, it is written as S, O, 3, 2 ions, okay, and thiosulfate, do they, no, they are not acidified, so converted to S, this is S4, O6, 2 minus, and if we balance we shall need a 2 here, and also to balance the charge then we shall put the 2 electrons this side. Then for our halogens, maybe let's use iodine. The iodine, and this is aqueous maybe, to give iodide ions. Okay, to balance you need a 2 here, okay, and to balance the electrons we shall put 2 here to balance the charge. So when you cancel this with this, then you have your general equation as 2 SO3, S2O3, aqueous, and then plus the iodine, and this is aqueous. We shall get S4O6, 2 minus, aqueous, plus iodide ions, aqueous, and there is a 2. So that is basically how the equation is going to be. So like we said, these halogens have a high oxidizing power. They are oxidizing agents. Okay, so they do oxidize different elements to their maximum oxidation states. Okay, That's good. So I think we have a question here. Let me check. Yeah, we have a question there. And I think we are stopping here. What is the time? It is even 49. So state what would be observed when chlorine is bubbled through a solution of iron 3 chloride. Hence write the equation. State what would be observed when chlorine is bubbled through a solution of potassium iodide. Can you drop the answers in the chat box? Even when you don't write the questions. Sorry, even when you don't write the equations.